Assalamualaikum and hi everyone. Bertemu lagi kita kali ini dalam lecture yang ke-10, topik linear regression and correlation. At the end of this chapter, regression analysis, we should be able to investigate the strength and direction of a relationship between two variables by collecting measurements and using suitable statistical analysis. Also, be able to find the equation of regression lines and use them where appropriate. For example, in a chemical process, suppose that the yield of the product is related to the process operating temperature. So the regression analysis can be used to build a model to predict yield at a given temperature level. In this regression analysis chapter, we will learn how to explore relationships between variables and how to measure the strength of such relationships. Here, we have three types of linear regression: simple, multiple, and multivariate. Next, in the correlation analysis, we should be able to evaluate and interpret the product moment correlation coefficient and Spearman's correlation coefficient to measure the linear relationship between two variables. Okay, here is the explanation for the linear regression variables. So we have here y is dependent variable and x is independent variable. Okay, for example, we have the mass x. So in x direction, we have the mass. And this mass x is known as independent variable or explanatory variable. And this mass is also controlled variable by the experimenter. Okay. And then for a fixed value of x, we have the response variable in terms of y, the dependent or explained variable here in y direction. So let's say we have y here in terms of length. Okay, so for any fix of mass here, we have a response variable or predicted variable in terms of y. Okay, and the resulting readings for y will form a normal distribution. Okay, so we will form a normal distribution. It is worth noting that in practice, the choice of independent variables may be made by the engineer on the basis of experience or prior knowledge, since this may indicate to the engineer which independent variables are likely to have a substantial influence on the dependent variable. Okay, here is an example of scatter plot diagram. The first step in establishing the degree of association between two variables. Example of pair of measurements which an engineer might plot are A. Volume and pressure, B. Acceleration and tire wear, C. Current and magnetic field, and D. Torsion strength of an alloy and its purity. In simple linear regression, data is described as y equals to beta naught plus beta 1 x plus epsilon. So what we have here, this part is called the error, also known as residual, which is the distance from the best fit line to the observed values. Okay, so the distance is also called the error because that's how far off the observed value from the best fit line. So the fitted model, we have y hat equals to beta naught hat plus beta 1 hat x. Okay, so this is similar to y equals to mx plus c, where beta naught hat is the intercept and beta 1 hat is the slope of the regression line. Here is the graphical representation of the fitted model. This is the equation that we have seen in the previous slide. Okay, that's the representation of the fitted model line. So the residual here, as I said earlier, is the distance between the best fit line, the blue line here, to the observed value. Okay, from here to here. Okay, here is the simple linear regression plots for the groove depth against the mileage. Okay, just a simple case like this. Okay, kat sini nak tunjukkan macam mana kita nak dapatkan the best fitted line, the red line ni. Okay, to do so is for us to able to minimize the residual here. Okay, the red line is got to be as close as to the real data. Okay, for each data point. So that is the best fitted line. This is what they means by minimizing the sum of the squared vertical distance between the fitted line and the real data. Okay, yang ni just the formula on how we calculate the error here, di, and then y hat here is replaced by this equation, and then here you get how to calculate the error. So the sum of this value need to be as minimized as it could be to get the good fitted line. The next 3 slides outline the derivation to obtain the equation of the least square method. However, I will not go into detail on the formulation development, but I will show you the example using Microsoft Excel on how to get the regression line model using the formula later. To simplify, the quantity S2x here is of course the variance of the x values, and the quantity Sxy is known as the covariance of x and y, and this will appear later again when we measure the degree of linear association between two variables. We have gone through on how to plot the data, to have a visual representation of the data, and then we have our regression lines, or the least square regression line, to represent the trend line, so that we can visually see the model that we are building. And then from the regression line we have the regression equation, which is the actual model that we are building, so that we will be able to analyze and even predict future values based on the sample values. We shall now look more into the strength of the relationship, or the goodness of fit, which can be described by the coefficient of determination, or R squared, and also the correlation coefficient, R. Here, the quantity of SSE, error sum of squares, is usually used explicitly in formula, whose purpose is to determine the adequacy of a linear model to explain the variability found in data. R is the sample correlation coefficient between x and y. For the simple linear regression, R squared is sometimes described as representing the amount of variability explained or accounted for by a regression model. For example, if after a particular calculation it was found that R squared equals to 0.884, we could say that the model accounts for about 88% of the variability found in the data. The correlation coefficient R range from -1 to 1. So R equals to 1 represent the positive correlation with all x, y lying on a straight line with positive gradient. Okay, so R equals to 0 represents the situation where either there is no linear relationship between the variables or that any relationship existing is non-linear. Where for R equals to -1, it represents perfect negative correlation with all x, y lying on a straight line with negative gradient. Here is the scattergram for positive correlation. R equals to 1, negative correlation R equals to -1, and no correlation for R equals to 0. The strength of the fitted model is also dependent on the estimation of variance sigma square. And the variance is the key in describing the goodness fit of our simple linear model. In general, the smaller the variance, the better fit, although you should note that it is wise to distinguish between poor fit and a large error variance. Poor fit may suggest, for example, that the relationship is not in fact linear and that a fundamental assumption made has been violated. It can be shown that the sum of squares of the error, SSE, can be used to give an unbiased estimator, sigma square, of S square via the formula. The number 2 here is because that in simple linear regression, we only consider 2 variables. After the strength discussion, suppose that a linear model is sufficient to describe the relationship between the variables. Now we've come to the part to use a significance test involving the distribution to decide whether or not y is linearly dependent on x. So we set up the following hypothesis, which is a null hypothesis. X is not linear predictor of y where beta 1 equals to 0, or the alternative hypothesis where x is a linear predictor of y where beta 1 is not equals to 0. Now let's see how come our null hypothesis is beta 1 equals to 0. If you remember that beta 1 in our fitted model of the regression line equals to slope. Okay, so that means the slope of the equation for the null hypothesis equals to 0. If we have a 0 slope, we might have a scatter plot, something like this. So there's no linear relationship between the x and y. It might be a no relationship at all. So that's why we mention for the null hypothesis x is not a predictor of y. So for H1, for the alternative hypothesis, when beta 1 is not equal to 0, we have a slope. So the scatter plot might be something like this. The positive slope, or maybe something like this, the negative slope. For a simple regression to become a multiple regression, we will consider more than one explanatory variables or adding the regressive variables. In this case, it will always increase the value of R squared. However, we don't discuss multiple linear regression in this chapter. We only focus on simple linear regression. As we are only focusing on SLR, so far what we have learned in SLR are as follows. 1. How to make a scatter plot to visually represent our data, and then how to graph regression line which visually represent our model, then our actual model which is the regression equation. We also learn how to determine the strength of the relationship through Pearson R and the R squared, the coefficient of determination. And this time we will learn whether the actual relationship is significant or not, because they might have a strong relationship, might be able to have a good regression line and a regression equation, but actually it's not significant at all. The relationship is negligible, no matter how strong it might be, because the strength might simply be due to the chance that we got from our sample. These are the steps that we will apply in our Microsoft Excel example later in the next video. Thank you.